part, I'll talk about doing parametric UQ on the CovidSim code. This is joint work by a substantial portion of the VECMA consortium. And so just to get started, so what is CovidSim? Like Derek already said, some of you will be familiar with this, but it's an individual-based epidemiological code. It's developed by the MRC Center for Global Infectious Disease Analysis at Imperial. It wasn't purposefully designed for COVID, but was adapted back in 2020 from an earlier influenza version. And in March of 2020, it was used to predict the effect of non-pharmaceutical interventions, so these NPIs. And then with the goal of reducing the spread of COVID in the UK. So many of you will be familiar with NPIs. These are things like social distancing, closing schools, house quarantine, things like that. And so what CovidSim does, it creates a network of these individuals, right? This individual-based code, and does that based on available population density data. And so you have this network which is like mimics the UK, and in this network, people can interact in 4 different places. So we have households, schools, universities are separate, and then general workplaces. There are quite a bit of these types of models by now, right? But this one is probably one of the more influential ones. So the key paper, which is called Report 9 for short, it has like more than 2,000 citations by now, but it was at least in part responsible for reorienting the policy back in 2020. Right? If you remember, first people were talking about herd immunity, but fairly quickly this was changed to a suppression of the virus. Right? And this model, the predictions coming from this model, was at least in part responsible for that change.
Could I ask you to click hide on that little warning button?
Sure.
Thanks.
There you go. Thanks. Right, so CovidSim, it's uncertain, like almost all codes, I guess. And we define these 3 general types of uncertainty. So the first one is parametric uncertainty. It's the one that we'll focus on most. This is the uncertainty that you get because you don't exactly know your input values. And I will denote Xi as the vector of input values. Perhaps a bit more fundamental is model form uncertainty, also called model error or model inaccuracy. And that is the uncertainty that you get because of the, let's say, the approximations that are made in the mathematical form of the model. And so in the case of CovidSim, you could think of missing epidemiological processes or missing place types. For instance, if elderly care homes are not one of the 4 place types that are included in the model, and you can't fix that by changing a bunch of parameters, right? And the third one, which is probably a bit less well known, I would say, is what we call scenario uncertainty. And that's the uncertainty in the scenario S under which the given model is applied. So you can think of boundary conditions or initial conditions, or in the case of CovidSim, the set of NPIs that you've selected. We denote small q to be the quantity of interest, so the output of the model. And that's a function of these 3 uncertain inputs. And we are going to focus mostly on the parametric uncertainty, and we're going to look indirectly at the uncertainty because of S. And to be a bit more specific, we looked at the robustness under input uncertainty. Robustness is a bit of an ill-defined term. It can mean different things to different people. Here we define it as how much the parametric uncertainty is actually amplified from the input to the output. So if you change your inputs a little bit and the variability changes a lot at the output, then your code is not robust. So this involves computing the mean and the variance over the inputs. So it's important to see that our results are still conditional on M, which is CovidSim, which we're not going to change, and it's also conditional on S. And to do that, you need to specify this input distribution. There are the two, let's say, problems in this case. In the case of CovidSim, there are 940 inputs, although in practice it's not that bad. But if you naively count every input in the input files, you get to this number. And the second problem that we face is you need the probably PDF for Xi, and this is not given, right? So you have to choose some reasonable input distribution. So the first problem, this 940 inputs, if you actually look at them, many of them are not relevant. There was quite a few of them that were related to vaccination, which might be relevant now, but wasn't relevant back when we wrote the paper. There's also quite a few were fitted to data, and we didn't touch those. And so we did a manual selection, which ended up with 60 inputs, which is still quite high. So we divided these inputs into 3 different groups. So the first one being intervention parameters, so anything related to the MPIs. You can think of the percentage of households that will actually comply with the quarantine. There's also disease parameters, like the latent period of the disease. And then there's a group that is related to the spatial and geographic nature of the code. And so what we did, we took those separate groups, each of them was roughly 20 parameters, and we did a separate UQ campaign on these. And I'll talk about this later a bit more, but this will allow us to identify the important inputs within this group. And then from the final UQ campaign, we just gathered all the important inputs, and that would be our final selected set of parameters. And in this case, it was a 19-dimensional input space. So that's how we deal with this. And the second one is, well, you always face with this, it's like selecting a prior, let's say. So we have to select some reasonable prior, and because we are by no means experts in epidemiology, we use the expert opinion. In this case, the developers from CovidSim actually helped us by selecting proper ranges for these parameters. So that's the range, but you still need to specify the form, right? And we used uniform inputs, uniform input distributions. There's some, pluses, some negatives to this. The advantage is that it's a good representation of lack of knowledge. If you look, for instance, at household compliance with quarantine, I think there's quite lack of knowledge here. You know for sure it's not going to be 100%. It won't be 0 either. But I couldn't tell you if 80% or 90% of the households will comply with quarantine. So this is really something you have to specify yourself, and I think there's quite a bit of uncertainty in that. So whatever you specify, you will still end up with some ambiguity. So for, let's say, our final campaign, 19 inputs, which still, in my opinion, is still quite a high input space. And if you look at EasyVVUQ, we have Monte Carlo, quasi-Monte Carlo, polynomial chaos, and stochastic collocation. These are all methods to propagate uncertainty from the input to the output. And none of these are actually ideal for these types of input spaces. So polynomial chaos, stochastic collocation are subject to the curse of dimensionality. I'll get back to that, but this basically means that you can't really apply them for more than, let's say, 8 parameters. And of course, Monte Carlo methods, they have a low convergence rate. So to fix this, we had implemented a different type of sampler, which is a version of stochastic collocation that is actually dimension adaptive. And so if you're not familiar with stochastic collocation, the basic building blocks of these methods are one-dimensional quadrature rules of m points. And m is then determined by the order of the quadrature rule. So I made a little picture over here for 2 inputs. And stochastic collocation extends the 1D rules to multiple dimensions by tensor products. But if you do standard stochastic collocation, the user has to specify the order of the quadrature rule. So in this case, for parameter 1 and parameter 2, I've selected an order of 2, which is a quadrature rule of 5 points in this case. And so a tensor product of 5 by 5 gives you 25 points in your stochastic domain. And then you evaluate CovidSim or whatever your code is on each of these points. And then let's say the central equation of stochastic collocation is this expansion over here. So your output Q is approximately equal to the stochastic collocation surrogate Q tilde. And that's an expansion over your code output. So this Q over here are these 25 code samples over here. And these are interpolated to an arbitrary domain by a tensor product of interpolation polynomials. So often these are Lagrange polynomials, but it can be something else as well. The problem is, however, that you can see that the computational cost is m to the power d. So in this case, 5 to the power 2. But if d is 19, you get 5 to the power 19, right? So for high inputs, these types of methods just not gonna work. So for this reason, we did dimension adaptive sampling, and this doesn't break the curse of dimensionality, but it does postpone it to higher dimensions. And the basic idea, I won't go into mathematical details. The basic idea is instead of just generating your sampling plan in one go, you do it adaptively. So you start with a single sample. It doesn't have to be, but usually you start with a single sample, which means you start with an order 0 rule. So again, if you look at just 2 input dimensions, if you start with order 0, then the final point will be just a single point. And then the second step is to actually look ahead in different candidate directions. So these are these crosses. So you evaluate your code at these 2 points, which means you have like a mini ensemble that you have to evaluate. And for each point, you compute some kind of error. There's different ways you compute this error. You can compute the error in the interpolation. So that's the error in this Q tilde. But you could also compute the error in some kind of quadrature methods. So for instance, you compute the variance in this point, compare it to the variance that you get for this point. You compute the variance here, and you compare it as well to this point. And then whatever direction generates the highest change in the variance, you add that to your sampling plan. So that's the second picture over here. So in this case, input 2 was more sensitive, so you add this to your sampling plan. And so you still have a tensor product. So a tensor product of 1 point with 3 points gives you this 3 points in the xi2 direction. And this just iterates, right? So here you refine again the second direction. And then in the fourth iteration, the first parameter gave the highest change in the output, so you add that. And one thing I would still like to say is that you can also refine multiple inputs at once. So if you have a, let's say, candidate direction, that it's not one at a time refinement. So this one over here, this X over here, it would refine both the first and the second input. Now, if you look at this in a visual way, for the case of CovidSim, you get something like this. The horizontal axis is just the iteration, so we have 60 iterations here. And these are a subset of parameters. These are actually the important parameters. And so you can see what's happening, right? So at iteration 0, everything is at order 0. The colors are, by the way, the order of the quadrature rule. And you can see that at the second iteration, this contact rate parameter gets refined to first order. So you refine that direction alone. Then in the third iteration, you refine the latent periods, then the delayed case isolation. And then you can see in this iteration here that you refine both the contact rate and the case isolation parameter at once. Right? And so this continues on and on and on and on. And the thing to take away here is that after 60 iterations, we actually did 200 in the end, but I'm just showing you the first 60. Just 7 of the 19 inputs are refined. And so you really pick up on a effective dimension that is much lower than the 19. Now each little colored block that you see is like a mini ensemble. It could be as low as 2 points, it could be 30 or 40, you don't really know, it depends on how many inputs you refine into what order they are refined, so you don't know beforehand how large this is going to be, but it's not that large. About this, so I can run EasyVQ locally. I use FET-HPC 3 to submit these mini ensembles, and we submit them to the Eagle computer at PSNC. Each COVID sample, it's like a moderately expensive code. It takes about 10 minutes for one sample if you use 28 cores. So not super expensive, but far too expensive to do on your laptop. So here are some results, and in particular, these are confidence intervals for cumulative deaths. And like I said in the beginning, conditional on a given scenario. So we picked some scenario which you call S1 from the Report 9 article. And in this case, R0, I'm sure you're familiar with this, it's 2.4. We have 4 different NPIs, but that's not enough because the model also needs to know when these NPIs have to be turned on and when they have to be turned off again. And so CovidSim operates based on the weekly number of new ICU patients. And so S1 is defined as when this number of ICU patients exceeds 60, the NPIs are turned on. And then the disease will drop a bit, and when they're below 15, the NPIs are turned off altogether. And that happens over a period of roughly 800 days, so let's say 2 years. And so these are the results in that case. They're pretty straightforward, I think. So the mean is the blue line. The purple shaded are confidence intervals, 68 to 95%. And this PDF that you see over here is the PDF of the final predicted death count after 800 days. You see, a mean around 10,000, but it's highly skewed, and a small but non-zero probability of 50,000 is also possible. Important to say that the yellow line here, that's the baseline Report 9 sample. So that's what was reported in this article without any uncertainty. And I'll get back to that later. The final thing to note here is that this over here, these green squares, is the data. So it's actual observed death count in the UK. And so despite this relatively large variance due to uncertain inputs, we're still not capturing the data well. And you could view this from 2 angles. One is that we're not incorporating the scenario uncertainty. And it turns out that that's actually quite important, and especially the initial conditions, right? These are fixed in my case. But if you want to capture that with this particular scenario, if you want to capture the data with this particular scenario, you need to make the initial condition uncertain as well. And that said, it is still possible to fit CovidSim to the data. And actually this paper over here by Ackland, it actually did that. So you can tune the model such that you can fix this data, but then you need to change the R0, and you need to change the initial condition. So what we're trying to say here is that, especially in the beginning, if you don't know much yet about the disease, the scenario uncertainty is quite significant. And you can see that by just changing the scenario. So this is exactly the same results except scenario S2. So here it's R0 is 2.6, and these ICU triggers are different. The data are still the same, so you can see that it's it changes the results quite a bit, right? We're capturing the data a bit now. The predicted deaths are much higher, and the skewness is not gone, but there's still a little bit of a skew, but much less than in this particular case. Well, we don't have to look at cumulative deaths. These are the confidence intervals for RT, so the reproduction number as a function of time, let's say. Same thing, so blue is the mean, it's very close to 1. Confidence intervals are the purple. And just to show you how this is formed, I'm plotting a single sample here as well. So the orange line, you can see exactly when the MPIs are turned on and when they're turned off again. So you get this sawtooth pattern. And when you take all the samples together, you get this uncertainty band on your RT, which lies roughly between 2 and 0.8. So these are, let's say, the uncertainty in the output. We can also do sensitivity analysis. And in particular, we looked at the first order Sobel indices. And again, this is conditional on a scenario. So if you're not familiar with Sobel indices, or in particular a first order Sobel index, it's just a measure of the fraction of the output variance that you can attribute to a single input parameter. And so if you look at this line over here, the triangles, you can see that's the relative spatial contact rate. So after 200 days, it's 0.4. It means that this parameter is responsible for 40% of the output variance. And you can see that these change over time, so they're not fixed. In the beginning, the latent period is by far the most important, but pretty soon after, this gets taken over by this spatial contact rate parameter. And the thing to note here is that if you add them all together, you get to roughly, let's say the stars, by the way, if you add all these Sobel indices together, you get to 0.8. So that means that the first order effects account for 80% of the variance. And if you want to account for the remaining 20%, you're going to have to change different parameters simultaneously. Right? The first order index only looks at the single input parameter. Same thing, but for scenario S2. This is actually doesn't change much. It's qualitatively quite similar. We computed this for another scenario as well and get the same results. So again, latent period in the beginning, most important than the contact rate parameter. And thirdly, the delay to start case isolation input. And you can see that even though we have a high dimensional input space, just these three inputs together, which is the red diamonds you see over here, they already account for more than 60% of the variance. So this is quite a general result. In most models, you will see something like this, I think. That just a small number of inputs will account for most of the variance. All right, so in the beginning I mentioned robustness. In our case, this means amplification. It could possibly mean damping as well, but the ratio of input to output variance. And so the general question here is that, is the observed output variance large compared to the amount of uncertainty that we injected in the model? And the Sobel index doesn't measure this. And so we looked at a new measure, we devised a new measure for this. And it's basically a ratio of coefficient of variation. So the ratio of the coefficient of variation of the output to that of the input. And so a CV, a coefficient of variation, it's just the standard deviation divided by the mean. And so that is a dimensionless measure of variability with respect to the mean. And the only problem we have here is that the dimension of the input is not equal to the output. Right? So we have D inputs. So over here we have an average coefficient of variation of the input. And we have N output points, in this case 800. And so this is the average CV of the output. And the CVR, the coefficient of variation ratio, is just these two divided. If it's larger than 1, we say that the code amplifies uncertainty. If it's smaller than 1, we say that it dampens the input uncertainty. This is the result of CovidSim for both scenarios. Well, the input distribution doesn't change. So for scenario S1 and S2, the input CV is roughly 0.2. So a 20% variability with respect to the mean of the inputs. The output does change. You could already see this a bit from the confidence interval. So this is again computed with the cumulative deaths. And so for scenario S1, it's 60%. So it means that the input uncertainty is amplified by a factor of 3. And for S2, it's amplified by a factor of 2. And so finally, one thing I'd like to mention is something that Dirk already touched about. So why should we care about this in the first place? And I think that models are used to inform high-level decision-making and probably will continue to do so, maybe even more than now. And I think that simulations without error bars paint quite an incomplete picture. And so imagine if you're in charge with evaluating NPIs or intervention scenarios. If you just have the yellow line, it paints quite an incomplete picture. You might come to the conclusion that after 600 days, roughly 10,000 deaths will occur if we implement this particular intervention scenario. But if you just take some reasonable input uncertainty into account, and I think in this case you really don't know many of these inputs, the same model with the same exact settings can also predict, was actually more likely to predict 10,000 deaths after roughly 300 days. But there's also a small but non-zero probability that it can occur in less than 200 days. So that's quite a bit of variability that you just don't get if you just have a single code output. And so just to conclude, we did an adaptive parametric UQ campaign on CovidSim. There are other ways of doing this, and we're looking at different machine learning methods to do the same thing now. But here we use dimension adaptive stochastic collocation. Naive count has 940 inputs, but you can bring this down to 60, and we iteratively brought it down to 19. And of these 19, just a small subset, 3, cover already 60% of the output variance. We looked at amplification, which it does by a factor of 2 or 3. And despite a relatively large output variance, you might still not capture observed data. So either you do continual fitting based on data, or we recommend to quantify the scenario uncertainty. And possibly if you have different models, you can also compute the model uncertainty in an ensemble. And so that's it for my case. If you want to read the paper, you can do it over here. It's published by now. And if you have any questions, please let me know.
Hi, thanks. So just to remind everyone, you can either ask a question in the chat or you can raise your hand as Rebecca Davidson has just done. And then you can unmute and ask your question. So Rebecca, would you like to ask your question?
Yes, thank you. Very interesting paper. I had 2 questions actually. First of all, just a small question. So you focus on the cumulative death cases. Yeah. Do you think the result will be different for the number of new death cases or for the confirmed cases?
If the results are different?
Yes, would the results be very different?
Yes, it is possible that different quantities of interest will give you a different picture. Let me see. Because, for instance, this CVR, right? It's based on the output. So if you compute the CVR, for instance, RT, you might get a different picture. So it is quantity of interest dependent, yes.
Okay. Yeah, interesting. So then for my second question, I have, if I understood correctly, the MPIs, social distancing and place closing were triggered by a certain threshold. Yeah. However, you also included other MPIs in your scenario. I think 2 others. So home quarantine and social distancing. Yeah, and another one. And in your figure, you display the cumulative cases with, on the x-axis, the number of days. So I wonder if these 3,000 evaluations were all evaluations where the scenario was chosen with settings where these MPIs were set from day 0 onwards, because these interventions were probably not likely all implemented at day 0. So my question is, in the scenario S2 that you selected, was the scenario set in such a way that the mentioned interventions were implemented from day 0 onwards? And a small other question is, did you take the on-off switch triggers into account in the uncertainty quantification?
I think that the triggers have to. I'm not an expert in CovidSim, but I see this as a black box. But the triggers, they, from the top of my head, they trigger only 2 of the MPIs. So we have 4.
Mm-hmm.
So the 2
Yes.
stay in place, and the other 2 are triggered on and off, based simply on the number of ICU cases. And
yes. Okay. So the other 2 MPIs were all well, static. They were implemented from day 0 onward. Okay.
Yeah, restrictions, I think maybe from a certain point onward, not from day 0. There's some sort of initialization phase, and you can probably see this in RT, right? RT is over here, so there's some sort of transient period, and over here you have the first activation of the MPIs, and then from this point onward, it's basically turning them on and off based on the MPIs.
Okay. Yes. Okay, so this, okay, interesting. Yeah, thank you.
We didn't take these, and the only way we took this uncertainty into account is by looking at separate analysis for S1 and S2. So we didn't do a full-blown scenario uncertainty analysis.
Yeah, I understand.
Yeah.
Great. Philip Eisenhower, would you like to ask a question?
Yes, so first of all, thank you both very much for the presentations and providing this toolkit. And I was just wondering what the role of sensitivity analysis tools is within the VECMA toolkit. So it didn't seem to be the focus, for example, the computation of Sobol indices or Shapley values, but now it showed up in the last presentation. So are those capabilities already available as part of the VECMA toolkit, or are they built by the researchers on top of it? Thank you very much.
They were already available. If you do polynomial chaos or stochastic collocation, you basically get your Sobol indices for free. You can estimate them in a post-processing step. So if you do your sampling, you can use those samples to compute the integrals that are required in these Sobol indices.
Is that
the only thing here? The only thing here is that there's different methods of implementing some. So for MC, it's different than for Monte Carlo, it's different than stochastic collocation. For polynomial case, also a bit different. And the problem with CovidSim, if you do a dimension adaptive campaign, we used again a separate method to implement these. So that's this paper over here.
Okay, and so the statement that you just made for the processing step coming out of VECMA, so that's also true for correlated input parameters?
Well, no, all these methods, they have an IID assumption.
Okay. Yeah, then I understand. Thank you very much.
Yes.
Thank you, Philip. I don't see any questions in the chat or any other hands raised. Just to remind you, you can ask about the CovidSim talk or the VECMA toolkit talk at the start. All questions are welcome. Perhaps there are no more, and that's maybe okay because we're running over time already. In that case, I'll just, no, don't see any more. Right, okay. Well, in that case, I'd like to thank very much Derek and Wouter for their great talks, and thank you all for tuning in. That was very interesting. Thank you, everyone.
Thanks a lot, everybody.
Cheers, thanks.
Cheers.